All right, welcome back everyone to our 5th session on dynamic topology. We're going to keep pushing forward with the Gordon-Whyburn method, really building our understanding of space from the ground up, one piece at a time.
So, up to this point, we've managed to construct these really fascinating things called topological spaces. But if you think about it, right now they're just kind of floating out there on their own, like isolated islands. To do anything really cool, we've got to connect them. And that leads us to the big question for today.
To connect these topological islands, we can't just toss a rope over and call it a day. Nope. We need a proper, rigorous mathematical tool. Basically a set of blueprints that tells us exactly how to build these bridges so that they actually respect the structure of the spaces themselves.
So let's get into our first set of blueprints. We need to formally define what these bridges even are. And in math, whenever we talk about a rule that connects one thing to another, we are talking about one of the most fundamental concepts there is, the function.
Okay, let's get into it. Here is the formal definition, straight out of Whyburn's book. A function is really just a law, a rule. It takes every single element in our starting space, which we're calling x, and it assigns it to exactly one unique element over in our destination space, y.
So let's just put that in plain English, right? The two key words here are every and one and only one. This means no starting points get left behind, and there's absolutely no confusion about where any single point is going. It's a super clear, totally precise mapping rule.
Now, not all bridges are created equal. Let's look at a special kind of blueprint. This is what we call an onto function. And this property tells us something really important about the destination of our bridge.
So, here's the crucial idea. An onto function guarantees that we cover the entire destination space. You can pick any point you want in space y, and I can promise you there's at least one point back in space x that maps to it. No part of that destination island is left untouched by our bridge.
All right, let's check out another type of blueprint, a one-to-one function. Now, this one puts a really strict rule on how paths can arrive at their destination, which gives it this special and very useful property.
And this slide just lays it out perfectly. A one-to-one function is like having a set of private, non-merging lanes. Every destination point has exactly one path leading to it. But on the right, you see what happens when a function isn't one-to-one. You can have multiple paths from the start all converge on the exact same spot in the destination.
Okay, so this is where it all comes together. This is really the most important idea of the entire session. We've defined the bridges, right? But now we have to ask the critical question. Are they good bridges? Are they topologically sound?
It is not enough to just build a bridge that connects points. The bridge itself has to preserve the essential structure of the space. It has to be what we call continuous. And honestly, without this idea, well, there's no topology. It's that important.
Okay, deep breath. Let's dive into this formal definition from Whyburn. Now, I know it looks a little dense, and you're probably thinking, wait a minute, I learned about continuity in calculus with limits and distances. Where are those? And this is the absolute genius of this definition. See, mathematicians realized that to really talk about the essence of shape, they needed a definition of continuity that didn't rely on measuring distance, one that would work on any abstract space. And this definition, using only open sets, is the incredibly powerful result of that search. So let's break it down.
What's so cool about this slide is how it turns that abstract definition into a concrete test. Think of it like a game of precision. Your opponent challenges you by drawing any target neighborhood V, no matter how ridiculously tiny, around a point in the destination. If the function is continuous, you have to always be able to find a source neighborhood U back at the start so that the function maps everything from your neighborhood neatly inside their target V. It keeps nearby points nearby. If there was even one case where you couldn't find such a U, it would mean that points that started close together were ripped apart by the function, and that's the mathematical signature of a tear.
So, what's the big deal? Why have we spent all this time building up to this one specific property? What's the payoff for understanding continuity?
This brings us full circle, right back to the central theme of our entire course. The whole idea of topology, this rubber sheet geometry, it's all about transformations that stretch and bend, but never ever tear.
And here it is. This is the aha moment. A continuous function is the mathematical rule for stretching without tearing. It's the guarantee that you can always win that precision game we just talked about. A non-continuous function, that's a rip, a cut, a sudden jump that just breaks the fabric of the space. That's what happens when you lose the game, because the space has been torn apart. Continuous functions are the only transformations we allow in topology because they preserve the fundamental connectedness of an object.
You know, we've done some incredible work today. We've defined our bridges with functions, we've specified their properties like onto and one-to-one, and most importantly, we've established the structural integrity requirement, continuity. These tools are now officially in our toolkit. So, the crucial question we're left with is this. Continuity is all about preserving nearness, but we've defined it using these abstract open sets. So what happens if we give our spaces a more concrete way to measure nearness? What happens when we introduce a concept of distance? Well, that is exactly what we're going to explore in our next session on metric spaces. See you then.